a few different concepts. The first concept being electric current. Electric current is going to be defined as when many charges move together through an object or wire. We refer to that as an electric current. Typically, these objects or wires will need to be made of conductors because we're talking about charges moving easily. The variable we are going to use for electric current is I. Why is it I? No idea. Don't worry about it. It is I. I is equal to the amount of charge that is flowing through our wire per unit of time. Our unit is coulombs per second or the ampere. No one ever writes ampere. Sometimes we refer to it as an amp, and it is abbreviated as a capital A. This is important. We always represent current as the flow of positive charges. Even though in reality it's negative charges that move in the other direction, we are going to think of the current as flowing in the direction that a positive charge would move. That's because, again, as I mentioned in a previous video, all of these charges, all of this work was done long before we knew anything about the atom. We knew that the atom was a thing, atomic theory was a thing, but we didn't know what it was made of. We didn't know protons, we didn't know neutrons, we didn't know electrons, we didn't know the nucleus model, we didn't know any of that. So Ben Franklin decided that a positive charge was what ended up being a proton, and he decided that we're going to put our currents in the direction of the motion of a positive charge. Next thing we need to cover is resistance. This is a measurement So again, this is a measurement of how difficult it is for charges to move through an element of a circuit. The resistance of that element is a function of the construction of the element and the operating temperature. So when I say that it is a function of the construction, what that means is resistance, which we are going to use a capital R for, rho L over A. So the Greek letter rho, we're going to use here to represent resistivity. This is a description of the material's resistance. For instance, metal has a very low resistivity. Copper, very low resistivity. Gold, very low resistivity. Other things like plastic would have an incredibly high resistivity. So it's just a measurement of how resistant is that material to actually allowing charges to flow. L stands for length. It's the length of the wire in the element. Sometimes the element is what we call a resistor, which is just a whole bunch of wire coiled up together. Sometimes the element is more complicated than that, but it's all going to boil down to this. wires, in reality, when we do all of our work, we're going to pretend that a wire has no resistance. But in reality, a wire is made of a material, so it has a resistivity, and it has a length. It also has A, which is our cross-sectional area of the wire. So, to kind of give us some analogies, resistivity is just how resistant the material is. L is the length of wire, A is the cross-sectional area. So if we imagine that our current is students moving through a hall, trying to get from point A to point B. If the hall is really long, it's going to take a long time to get there. That hall is relatively resistant to the student moving. And if but if the hall is very wide, has a large area, it's going to decrease the resistance because the crowd is going to be spread out more. So a large area decreases resistance, a small area increases resistance. A long length increases resistance, a small length decreases resistance. The unit that we are going to use for resistance is called the ohm. It's named after a guy who did a lot of work. We're going to talk about his law later. And we're not going to abbreviate with the letter O. The letter O looks too much like a 0. And we don't want to say 50 and think that's 50. We want 5 ohms to be obvious. So we're going to use the Greek letter omega. We've already used the Greek letter omega. The lowercase omega looks like a W, and we've used that for angular velocity. But the capital letter omega looks like this horseshoe. That's our unit for resistance. Now, I also said that it's a factor of the operating temperature. We're not going to look at an equation for this. We just need to know that resistance will increase as temperature increases. This might be counterintuitive because temperature is speed of particles, and if the particles are moving faster, then surely the current should move faster. But in reality, this temperature is the random motion of particles. If we have particles moving around randomly in our wire, faster and faster and faster, it's going to be harder for our electrons to move through it smoothly. So again, going back to the analogy of a hallway, imagine a hallway where a whole bunch of people are bouncing around it randomly. It's going to be pretty hard for you to walk down it. The last thing that we're going to talk about is called the electric potential. We are going to talk about electric potential at a very, very basic level. If you take AP Physics 2, we talk about electric potential in a more rigorous, complete way. Our understanding of electric potential here is going to be very surface level. And electric potential, I have seen it happen time and time again on FRQs. Students are confused by, and students use it incorrectly. This is electric potential, not electric potential energy, not electric energy. It is electric potential. It is the potential to move charges. And we're going to call it voltage. A lot of times we don't really refer to electric potential in its raw form. We don't say that this has more electric potential than that. We're instead more worried about the electric potential difference as we move through a circuit. This is how much the potential changes in an element. We're going to use delta V to represent this electric potential difference, and it's equal to IR. This equation here is the most important equation for the electric circuit unit. V equals IR is as important as F equals MA. Our unit is going to be the volt. Our abbreviated with a V. This is one of the few times where the variable and the unit are both the same letter. The best analogy we have for electric potential is elevation. If I lift something up higher, it has the potential to fall. I could describe that as having potential energy, but here I'm just describing it as having the potential to move. Something more elevated has more potential. If I compare something that is, let's say, 2 stories up to something that is on the ground floor, the thing that is 2 stories up would have more potential to move. And I can measure that difference in potential by just measuring the difference in height. That's kind of what we're doing with electric potential. We're measuring how much the potential to move charges will have changed. Now, these 3 things, current, resistance, and electric potential, voltage, combine together to form our understanding of electric circuits. We are only going to be focusing on DC, or direct current circuits. AC, or alternating current circuits, are a little bit more complicated and not really that useful to us here. DC circuits are much more basic. It means that the current goes in one direction only. So electric circuits are just operating under the understanding that when a potential difference is applied over an element, current will flow. So when I take a source of electric potential, so a potential source, and I connect it to either end to both ends actually, of an element, current will flow through the potential source and into the element and then back into the potential source. The word circuit comes from the word circular. It must be a circular flow. It must be a closed loop is the phrase that we're going to use. So our potential sources are batteries, or what we call power supplies. A battery you're familiar with, AA, AAA, 9-volt. A power supply is something that you would plug into the wall and would turn it into a steady source of electric potential. They all have a positive and a negative end. The side that is positive is where the current will flow out of. The side that is negative is where the current will flow into. In order for our current to flow, it has to go out of the positive and into the negative. Current flows out of the positive and into the negative. You can't have current flowing out and not also flowing in. You can think of the potential source as, a lot of times we like to use analogies for electric circuits, and that's great, but all analogies have flaws. So an analogy for this could be, for electric circuits, could be a river. So water at higher elevation has potential to flow downhill. It flows downhill in a current. The speed at which it flows is analogous to the current until it gets down to the bottom. The potential source, the battery, you can think of as a pump that drives water from the bottom to the top. If the pump stops working, if we stop pumping water in at the bottom, we're going to stop pumping water out at the top. So we have to have a current flowing into the negative and out of the positive. Now, I've used this word frequently, elements. This is just our generic word for any resistor or light bulb or even a wire, just anything in the circuit. Now, to draw circuits, we're going to use some symbols. I'm going to draw this circuit out first. That was a terrible one, but oh well. So our first symbol here, this is our symbol that we're going to use for our battery. We use the same symbol for a power supply, but we're just going to always think of it as a battery. You'll notice one of these lines is short and one of these lines is long. The long side represents the positive end of our battery, and the short side is the negative end. This symbol right here, we don't use it that often, is a light bulb. A light bulb is an element that we use a lot of times when we are doing labs with circuits, but not a lot of times will we use a light bulb in our circuit diagrams for doing our math. This right here is a resistor. A resistor is a material that, as current flows through it, it resists that flow of current. Typically, resistors are made of wire that's been coiled around and covered in some form of, usually some form of ceramic. Light bulbs and resistors behave very similarly in circuits, so we're typically going to think of only going to focus on resistors as elements of a circuit. Now, what I said before about potential source, current flows out of the positive. So we have a current flowing out of the positive, around through the light bulb, around this bend here, in through the resistor, back around, and into the negative. A circuit must be a closed loop. For current to flow, it must be a closed loop. If your loop is not closed, current will not flow. This brings us to measurement tools. The two big ones are the voltmeter, which measures the potential difference across an element. Voltmeters need to be connected to both ends of the elements in question. So one end of the voltmeter will be connected to one side of the element, the other end of the voltmeter will be connected to the other side of the element. Then we have an ammeter. It measures the current flowing into or out of an element. It needs to be connected in the flow of the current. So it needs to be in between the resistor and the element and the rest of the circuit. So if we have our simple circuit here, there's our battery, positive end, negative end. We have a wire, and I want to measure the current coming out. I will need to put my ammeter directly there. I want that current flowing straight into one side of the ammeter and out of the other. And then the current flows through a resistor. And I want to know, how much does the electric potential drop in that resistor? I'm going to connect my voltmeter to both sides of this resistor, and that will tell me how much potential is lost in that resistor. In order for anything to actually happen, I have to close my loop so that my current can flow. Knowing how to connect a voltmeter or an ammeter is important. A lot of FRQ questions, a lot of lab FRQ questions have required you to have some basic understanding of the measurement tools and how to connect them. There is a third tool, but I will get to that in another unit. Voltmeter measures electric potential, ammeter measures current, and then the third meter will measure resistance. But that is it for our basic introduction to electric circuits. In the next video, we will get into actual math involving these circuits.